So now let's look at the Laplace transform of the sinusoidal function. So we've seen from the previous video that if we find the Laplace transform of e to the I omega t, we get 1 upon s minus I omega, and e to the minus I omega t gives us 1 upon s plus I omega. So we can use this little identity that we've seen previously for the cos omega t. So cos omega t is e to the I omega t plus e to the minus I omega t upon 2. So it means that we can put the values for the Laplace transforms for these into this equation. So you're just going to have a half of s minus I omega for the e to that plus I omega part, and a half of s plus I omega for the e to the minus I omega part. So we'll take a common factor here at the bottom line. So the common factor is going to be s minus I omega times s plus I omega. So in the top line it's going to give us a half of s plus I omega plus a half of s minus I omega. So that means that whenever we multiply the bottom brackets out, we'll get the s squared, the plus I omega will cancel with the minus I omega, and then we'll get our value over minus I omega squared minus I squared omega squared. So that's just going to give us a plus omega squared on the bottom line. So the Laplace transform of the cos omega t is going to be simply a summation of this. So it's a half of s plus a half of s, which is just the s, and again it's a half of the plus I omega and half of minus I omega. They just cancel out. So finally you're left with s upon s squared plus omega squared, where the real part of s is greater than 0. So let's go and we'll look at that in a pole zero diagram, and we'll also look at it in Matlab. So you can see this here in the output from the Matlab simulation. We're going to have the sigma axis here and our I omega axis here, and we have a pole positioned at the plus 1 in I omega axis and minus 1 in I omega axis, and there's actually a 0 in here as well, but you'll be able to see that better when we look at it live in Matlab. So again, we'll use this L1 function, and we're interested in the cosine function, so we can write that as s upon s squared plus 1. So we'll have this little function in the resources section, so you can go and copy and paste that if you want. So let's have a look at that now. So it's just as we had seen in the slide. We have two poles at plus and minus 1, and we have a 0 at the origin. So we can do a similar analysis with the sine omega t. We have our two functions here which we generated in the previous video, and we've got the sine omega t given by this identity, e to the I omega t minus e to minus I omega t upon 2i. So when we put the values in, we're going to have 1 upon 2i upon s minus I omega plus 1 upon 2i s plus I omega. We take the common factor, s minus I omega s plus I omega, gives us 1 upon 2i s plus I omega minus 1 upon 2i s plus I omega. So whenever we multiply these out, we get the s squared, the I omegas cancel, and we get the omega squared here as well. And whenever we add these up, we're just left with the omega, and that's for the real part of s greater than 0. So we can say then that the Laplace transform of our sine omega t is omega upon s squared plus omega squared, where the real part of s is greater than 0. So let's go and have a wee look at that again in a graphical approach using Matlab. So we've seen from the previous slide that the function was omega upon s minus I omega s plus I omega. So we can say that we're going to have a pole whenever s minus I omega equals 0 and s plus I omega equals 0. So we're going to have a pole when s equals plus or minus I omega. So it's very similar to the cosine example. The only difference here now is that we no longer have a 0 because there's no s term in the top line. So we're simply got two poles separated by plus and minus I omega. So this is it shown here. So these are the two poles on the sigma and I omega plane. So in Matlab, again, you can get an output here in Matlab. So we have I omega along this axis, sigma along this axis, and we've got our two impulses at -1 and +1 in the I omega axis. So let's go ahead and we'll have a wee look at that live in Matlab. So now we'll look at the sine function. So the sine function is going to be given by 1 upon s squared plus 1. So if we put it within the little function L1, it will produce the function in the complex plane. So let's have a look at that. So there's a function in the complex plane. It's two poles. There's no zero this time, and they're centered at a value of minus 1i and plus 1i. So that's all there is for this video. We looked at the Laplace transform of the two sinusoids, the sine and the cosine. So I'll get you on the next video. Goodbye.